Hello and welcome to a computer science lesson. Yes, this is not a Solana tutorial, but it's a preparation for a Solana tutorial because I want to work with assembly, and then I thought, well, 90% of devs will not be able to follow me if I just start coding in assembly, so I kinda gotta do some basics before that. So today we're gonna have a look at the von Neumann architecture and basically learn how to code in assembly on a very simplified version of an actual computer. So if you already know how to code in assembly, this could be a refresher, or you can just skip that video. But if you only ever coded in high-level languages, or say languages that we actually still use today, then maybe this could be interesting for you. And I'm really trying to make this one a quick video. So shall we get to actual Solana stuff? But you know me, I like to talk. And I'm trying to get you some of my knowledge that I learned in the 10 years of studying and teaching computer science at university in a condensed, compressed form, just so you have a little bit of background and can follow along if we do assembly stuff. That's my goal. So let's do it. And in order to do it, I found this tool, the little man computer, and we're just gonna immerse ourselves into this thing. And I'm gonna teach you the basics of how a computer works on this very simplified version of a computer. The little man computer. This is very, very simplified. This thing was actually developed in 1965. And in computer science terms, that is old. Like, real old. So you can imagine how this is not the high-tech new stuff. This is from 1965. Wow, 1965. Holy shit. I don't like to have this space down here though. This doesn't look good. Now I'm sitting all the way in the data. That's fine. Okay, welcome to the LMC, the little man computer. I haven't actually worked with this before. I just thought it's helpful and I kind of like the background color. Let's have a look what we see here. We have a bunch of memory, the random access memory, the RAM. We are simulating a computer here, and those are the building blocks. We have the memory, then we have the CPU, the central processing unit. That's the thing that does the calculations. And this is a very simplified version again, because inside the CPU there's also a bunch more for arithmetics, and it has a bunch more registers. Essentially, this is a one register CPU here, depending on what you count as register, or maybe 4 or maybe even 5, whatever, however you count. Then we have input and output somehow. So somehow we get data in and get data out. That's not too relevant for us. And we can write a program in assembly. So that looks like assembly code. And it's encoded as well for us humans to read. And maybe I should even go another step back and discuss the von Neumann architecture. The kind of innovative thing that happened with von Neumann architecture is that we put our program code into our memory. So when we build the chips, we don't already pre-program them for them to always do the same thing. No, we make it in a way that they get their instructions from the actual memory. And that's how we get programmable computers. That was the cool thing with von Neumann. And this is years back. I mean, nowadays you expect your computer to be programmable, of course. But we're talking early days computing here. So yeah, von Neumann architecture, where we can load a program into memory and then we have the program here. Now, what is here? Basically, at those memory locations, we have some values stored now, and those values represent operations for the CPU. So the CPU can read that. That's called fetch. Then it tries to understand what it should do. That's the decode. And then it actually does the thing that it's supposed to do. That's the execute. So it's a fetch, decode, execute cycle. If you ever did a computer science lesson, you might have heard that. The fetch, decode, execute. It keeps going like that. So basically what's going to happen is it has this program counter. So it remembers where in the program it currently is. Right now it starts at 0. So what it will do, it will fetch whatever is at RAM 0, load that into its registers, and then decode what that would mean, and then execute that. And then it increases the program counter and continues at the next thing. That's basically how this works. And so when we write programs directly for the CPU. We write directly those opcodes telling the CPU, hey, CPU, do this. And at the next step, do this. Then higher level languages abstract a lot of stuff away, because here we really need to go step by step. Read this, add this, write that to memory again. And in a high level language, you would just write variable name plus equals this number. But when that gets compiled, it gets compiled into several opcodes that the CPU can then actually do. And those opcodes are then also what is actually stored in the executable file. And for us on Solana, that's then what is in the actual program account. When we decode that, we'll see those opcodes. And we'll need to have an understanding of those in order to be able to program, like very low level. We're talking really, really low level now. Really low level programming. But I just want you to understand this, because otherwise you won't be able to follow when I go through it on Solana. So we've loaded a program into memory. We can then execute that program by clicking here. And that thing will work with input by querying something. So the first thing that it will do is input. We can also have a look at the table. Those are the things that it supports. Input, retrieve some user input, is opcode 901. That's why we have 901 in here. So when it reads that, maybe let's go step number 1. Oh, it requires some input. Here you go. Okay. Then we see the address register is 0. The data register is 901, so that's what it read. So when my program continues, it reads from memory and gets that into the CPU. So those are those two registers. So we have the memory address register, we have the memory data register, and then we have the, what's that? I think current instruction register. So the current instruction is 901. That's what it currently performs. And then we have this one real register that we can actively use, and here it just calls it the accumulator. That's basically the CPU internal register for, operating with the data. Like when we read input, then we read input into the accumulator. And then the next step here, when we do the 902, then it will write that into the output. Boom, now the accumulator got written into the output. And that's a simple countdown timer here, but that's already a more complicated program. Maybe we should start with something simple, just so we understand what all of those things do. So let's write our own program. Let's reset all of this. And it's always that thing, the mnemonic that we need to write to get the corresponding opcode. So basically that's what we write, which translates to this in machine code. And on a real CPU, this would be, binary and would also be longer. But usually each single instruction here has a combination of opcode and then an actual, parameter or value or whatever. We don't see it for the input or the output or the hold, but for load, for instance, if you want to load some contents of the memory into the accumulator, we need to tell it where it should load from. And so we say 5 for load, so that's the actual opcode, and then XX for where it should load from. So for instance, if I want to load this here, memory location 42, I would say load 42, which would translate to opcode 542. So if we load that program, we see that's opcode 542. And if we would actually run this program, well, it would load 0 into my accumulator, unless we actually have data here. If my data was 69 and I run this, boom, suddenly we have 69 in our accumulator, and the program counter hopped to memory address 1, where the actual instruction is 0, which means hold. So here the program should then end and be like, okay, I have been told to stop. But this simulator lets me keep going anyway. Can follow so far? So what other operations do we have? The opposite of load, we can store. So whatever is currently in our accumulator, we can store it to an address. So we load 42, then we store it to, 43. So if I have the 69 here and I run this, it loads the 69 and then, oops, I should have compiled and it's not compiling, it's just deploying. So it loads the 69 and then it stores the 69. So now we have 69 in memory location 43 as well. Cool, quite boring. Let's maybe do something to that data. And this simple instruction set just has add and subtract. Proper CPUs have a lot more instructions, like with bit shifts and multiplications and whatnot, just to make it easier. Because if you wanted to multiply with that, you would need to constantly add or whatever. But this simple instruction set just supports add. So this CPU can just add and subtract. That's all it can do. So we got to work with that. Let's read. Adds the contents of a memory address to the accumulator. So basically, in this simple example, if I say add, 41, then it adds whatever is written in here to the accumulator. So let's deploy this. Write 69 and 1, and then we step through. We load 69. We add the 1, so then we have 7, and then we store that to 43. Simple program. It gets a bit annoying to always manually write into memory. We can define data. We do that with that dot used to associate a label to a free memory address. An optional value can also be used to be stored at that memory address. So we can label stuff, because for now I'm hard coding those 42, 41, 43. I can say the label for what I currently have in 41 is add me, which is data and is 1. And then let's name it initial, which is data, which is 69. And then I load the initial and I add the add me, and then I store it to result. So that's working with labels then. Let's see if that also works. Now we see that the data fields have been deployed, so they are part of my program now, the 1, the 69 and the 0, but really they are not opcodes. So my program will fail here, or actually, well, we'll see what happens. Let's step through it. We start at 0. We load, so we have the 69 in the accumulator. Next step is 1, 3, which is add whatever is in 3. And in 3 we have 1, so it's 70. And then the next step will be 35, which is store at 5. Boom, at 5 it stores the 70. And now, and this gets fun, it interprets that as a program instruction, because my counter is set to 3. What will it do? 1, well, it will try to add something, but I don't know what, probably 0, or say this is not valid. This could also be. Maybe it would need to be 10 for it to work. Maybe it ignores that. 69 would be what? Branch if, branch always, jump to 9. Yep, now it jumped to 9. Program counter to 9. We didn't discuss the jumping yet. But basically, that's not what should happen. So actually, I should put a halt here, such that we have an actual 0 between the actual program and the data, such that it returns here. And then it would stop here. If I run it, then it would stop here. So far, so good. I think that's relatively easy to understand. We can load stuff, we can do operations, and we can store stuff. Now we get to the interesting parts with actual program flow. Because for now, we always step further. And so basically we have one sequence of things that we can do. But in our programs, we might want to have loops Or we might want to have conditions, like only if that is the case, then I want to execute something. And for now, with those operations, I can't really do that because I need some kind of decision making. So that's where those branches come in. There we have a conditional if positive, there we have a different conditional if 0, and there we just have a jump, always jump. With that we could do an infinite loop. So I can say before you halt, branch always to memory location 0. Then it runs indefinitely. So now if I deploy this and I run it, then it just runs in this loop and keeps doing the same thing. Doesn't change anything because I always load the initial, but I could change my program, load the initial initially, store the initial into the result, and then load the result again, and then jump back to 2 where we loaded this result. Then it will first load the initial and then always the result and keep increasing that. So we see here into what is now the data for result, this is being increased and increased and increased. And because this is a bit annoying, knowing where in the code that is, we can again give that a label. So here I call it loop, and then I say here loop. That should translate into the exact same thing. I think nothing changed now. And if we run the program, it's still the exact same because that translated branch translated into 6-2, so it jumps always to 2. Nice. So far, so good. So that's the branch always with which we can do a loop. Now we just need a conditional, and then we're Turing complete. And we can make decisions with the branch if positive or if 0. So for instance, if I want my counter to stop at 100, how would I do that? Well, a bit complicated because we are in assembly, but I will store my stop at 100, stop it. And then basically I will subtract the stop at, so I'll subtract 100. Does it do negative numbers? Let me test if that thing does negative numbers. I have no idea. We load it, we store it, we load it, we add it, we store it, and then we subtract, and then we're at minus 30. Okay, so basically now I can be like, well, if we're positive, then I'm jumping out. So that's basically the I mean, it's a really bad implementation. You can optimize later. What's it called? Branch if positive, we go to, let's say, end. We go to end, and otherwise we loop back, which is a bit weird. Maybe I should change my logic such that I only have one jump, but it will work. Let's see. Let's run it. It keeps adding to my results field until we get to the 100, 98, 99, and then it's 100, and then it jumped out. You see, because then the accumulator was 0, and if it's 0 or positive, then the branch positive will do the thing and actually jump to the end, thereby not doing the other branch. And if you've coded in C or similar languages, this branching is basically a go-to. You might know this as a go-to because that's literally what it is. Just that in higher level languages, we try to, not use that because it makes the code really difficult to read and understand. So we prefer, recursions and for loops, but under the hood, that's what's happening. It's just branching. Yeah, so can we optimize that code such that we don't have 2 branches here? Because that's really difficult to understand for somebody who didn't just watch me develop it. I would need to first load the stop at and then subtract what I have in the result. Load what I have at stop at, then I load the 100 and then subtract the current result. And again, in a real CPU, you would have several registers and then you would just work with those registers, which would make it a bit easier. But then I wouldn't need to branch to the end. But if that is negative, now I branch to the loop and then I save the branch always. So I just have one branch. But does that make it easier to understand? I'm not sure. However, it will still work. Simulation doesn't work faster. Poor little computer. Okay. 99 and 100. And oh no. I'm off by one. Shit. Oh yeah, because at 0 it still continues. So if the calculation of the subtraction is 0, then it still continues. So I'm off by 1 now. But then I would just decrease that by 1 and it would also be fine. Doesn't matter. So that's basically how we write programs in assembly, right? And those are the things that we can use. But I think that's good enough for me. I hope that gives you a basic understanding of what is coding in assembly is really like. We're basically really on a very low level tell the CPU what it should do, like really step by step, and we can write the registers and we can then store that into memory, and then we can load stuff from memory, and then we can do operations on it, and then we can jump to another position in our program, and with that we're basically able to develop anything. It's just a lot more complicated than on a higher level language like C and higher level. Yes. Higher than assembly, because that just abstracts some stuff. But that's why we need to compile C code, compile it down to assembly, and then the assembly code gets translated into actual machine code with, the bytes that is still human readable. That gets then converted into those actual bytes, and that is then executed. So those are the steps. And yeah, I'm motivated to actually do some assembly coding on Solana now. So if you're up for that, here it is. Let's go do it. And I hope this little computer science lesson was helpful. If it was, give me a like, make sure you subscribe, and I'll see you when we do more Solana stuff. Or maybe another computer science lesson. We'll see if we need them.